So to start this afternoon, a bit of things about the allocation theory in farm animal. So my name is Laurence, and I'm working in the same unit as Nick, Mozart. So it's an INRAE unit based in close to Paris. And basically, the idea is to see how this theory can be useful in modeling trajectory and feed efficiency and resilience in farm animal. Because I think, and I would like to thank Masoud, who did a very good introduction this morning. Theory is important when you are going for mathematical modeling. So, and especially when you are dealing with feed efficiency, and it's a very complex property. Here it's a basic scheme of what is efficiency. Finally, we are talking about a property of an animal to acquire a resource and transform those resources into a product. That could be meat, milk, wool, whatever. But we are talking about this transformation process. And first thing, it has already been said by Ellie yesterday, it's difficult to measure because we need to know dry matter intake. So that's the first difficulty when we are talking about feed efficiency. But I'm a nutritionist. I mean, my background is more in nutrition than genetics. Feed efficiency is also, the whole transformation process is also the result of a lot of different physiological sub-processes. Because once the animal intakes some dry matter, you have all the digestive processes, which are more complicated in ruminants, because the rumen is a very important organ, and you may have different efficiency at this level, digestive efficiency, mainly. Then once the food is digested, the food is going into organs, so it's nutrient partitioning. Each function can take part of the nutrient absorbed. And then each tissue has its own metabolism to finally elaborate some products, milk or meat. So this is quite complex. So feed efficiency, first difficult to measure, and then substrate combination. So finally, because you can be efficient by combining different aspects of all these traits. The whole thing is dynamic and time dependent, so it's another level of complexity. And you may have some trade-offs among all those different processes that are below the general property of feed efficiency. So how can we implement a sustainable genetic selection for this trait? And I think that was the whole target of Smarter project. To do this sustainable genetic selection, we need to be able to evaluate what are the long-term consequences of selecting for feed efficiency. If we are selecting animal right now on some traits that we're supposed to be related to feed efficiency, what's going to be the results in the long term? Is there any side effect of what we are doing now by selecting our animals? And are we selecting the mechanisms we want? Because finally we are playing with phenotypes that are measurable, observable, but what is behind those phenotypes? And an important question is, high-merit animals for feed efficiency, are they able to accommodate different environments? And are they still resilient? So that's the general picture of my introduction. And to address this key aspect, my approach is based on a simulation model that is dynamic and process-based, so mechanistic model, if we are back to the type of models that Masoud presented this morning. And those models, this model, incorporate allocation as the conceptual framework. That's my research avenue. It's not the only research avenue, but this is the one I will present this afternoon for you in this training school. So my talk is in two parts. We will see in the first part, where does allocation come from? It's a concept that is coming from ecology, so I will just give a bit of background to this allocation theory. And in a second part, we will see how this concept, coming from ecology, can be integrated with more classical nutritional approach. So let's start with resource allocation theory in ecology. So in ecology, basically, it's a bit like for geneticists, variation is the key topic of interest. And we know that different life history strategies exist. Here you have a mouse. And it's random. I am with the elephant comparison, Masoud. But you can see that these two species, they have very different life history. It's very basic, but I mean, if you did a bit of biology in your degree, that's what is in the natural environment. And we can see that for the mouse, lifespan is short. Age at maturity, sexual maturity is earlier. There is a lot of parturition per year with a high litter size. While for the elephant, that's more or less the opposite. It's a big animal with a long lifetime, late age at maturity, not so much parturition per year, and only one progeny per offspring per parturition. And finally, to explain what happened between these two species, you can look at how they deal with reproduction, survival, and growth. These three elements are a way to explain the differences we may observe among animals and species. So this variation among organisms is not very new. I let you check the old reference from Darwin, but for geneticists, I think it's maybe more this part that is interesting. Like, this theory explains the covariance we may observe among traits. So here it's an illustration of the relative life expectancy on the x-axis and the relative age at first reproduction. So you can see the covariance among those traits that reflect the difference in the different life histories of those animals. And generally, ecologists say that it's slow, fast continuum strategy. So it's not just too extreme. You can find animals that are all along the gradients of strategy. And all these different strategies may be explained in ecology by trade-offs in resource allocation. So basically, what you invest for growth, you will not be able to invest for reproduction or survival and so on. So, okay, a trade-off, very, very close to allocation theory. It means that if you increase X, you will decrease Y. So very simple saying like that, but applied to farm animal, it's a bit more complicated. So that's the little graph I put on the top right of the slide. And it's just to say that the Darwinian demon doesn't exist. It means an animal that is able to live forever, reproduce 100% times he tried to reproduce, and having a lot of offspring, this doesn't exist because you need to allocate resource, and there are some trade-offs among traits. And this concept has been used, it's just an example, by Cody in 1966 to explain variation in clutch size in birds. The clutch size in birds, it's generally a trade-off between avoiding predator and competition for resource. So that's one example of how people in ecology are using this allocation framework to explain some animal strategy. So life history strategy is a genetically inherited pattern of resource allocation. You're able to survive in an environment because you belong to a species that has been selected in this environment, and you come with this allocation strategy. And there are some cost benefits to see which strategy is the more optimal in an environment. But generally, everything is about maximizing fitness. So it's a bit like in genetics, when you want to have the best breeding value or maximizing the breeding value for an animal. So resource allocation theory in ecology, it's a very, very short introduction. You may find some entire books on this theory. But it's a framework that is useful for describing trade-offs. This is completely linked to this. Also very useful to explain and to understand interaction among traits and among function, Remember the mouse and the elephant with growth, survival, and reproduction. It's a framework that is useful to understand variation among individuals. And it's also useful to predict the long-term effect on fitness. So if we are back on the complex features I was talking about at the beginning of my talk on how can we sustainably select animals for improvement in feed efficiency, this is why we started to look at this theory and trying to incorporate this in our work on feed efficiency. Is that okay? You are not the digestive. How is your acquisition process right now? Please try to push energy in your brain. I know that this is not easy. Finally, I've got the easiest position because I have to stand and speak, so I will not fall asleep, hopefully. And yes, this interest of the resource allocation theory, it's not only my lab that did that. You have a very interesting book from Wendy Rowe, published more than 10 years ago now, Resource Allocation Theory Applied to Farm Animals. So it's not new, the interest of this theory, but that's a very nice book. Okay, so now we know where does resource allocation comes from. So we switch to resource allocation in animal nutrition. So basically, animal nutrition is to understand how to feed animals to obtain products. There is obviously a link with feed efficiency. And the background of this area is really energetics, and to understand how much energy is lost or retained by an animal. So historical approach were about understanding gas exchanges, heat production on the animal, being able to evaluate the food that the animal are eating related to their requirement and expenditure, and also understanding the causes of expenditure. Just an illustration, if you look at a female rabbit doe, she will spend half of the energy intake into lactation, while it's much more 70% for dairy cow. So in nutrition, it's important to understand these big sinks of energy, so these causes of expenditure. And saying that, very quickly comes the question of nutrient partitioning. For animal nutritionists, it's really important to understand how nutrients are partitioned among function. So here is the link with resource allocation theory. And this nutrient partitioning has been the core of the development of feeding table. How much should you feed this cow or this sheep or this goat that is growing or not, first lactation, second lactation, litter size 1, 2, 3, and etc. And the first system were quite old, finally. And the concern about nutrient partitioning or resource allocation, even if nutritionists didn't say that, it was more or less the same. You can see here a few old schemes about this interest for nutrient partitioning. So here it's a scheme from Hammond, 1947, where the question was, okay, there is the bloodstream, the nutrient, and how the different functions, so brain, bone, muscle, fat, mammary gland, placenta, fetus, how all these organs are competing to absorb nutrients from the blood. Another scheme here, Owen, 1978. So the same, you have intake, waste, so back on the digestive efficiency I was talking before. So the leftover is fueling the maintenance of body function, and the leftover with this partition valve is going into milk or body reserves. So you already have this vision of how nutrients are channeled to the different function. And the last one, I think it's my favorite one, from Weiner, 1992, with this barrel model. Maybe it's because I'm French and I drink wine, so the barrel model is more attractive. But the idea that you have foraging to get resource, then digestion, absorption, and then heat, work, tissue. So this question has been there for a long time. And what is really interesting, so here it's an extract from a paper from Kellner, 98, so quite old. So one cow gave 1.85 kilograms more milk and 29 grams more fat. They were analyzing an experiment where they checked the cows for different aspects of production, milk quantity and composition. So another cow, for the same diet, another cow gave 2.24 kilograms less milk, but with 66 less fat, and so on. I'm not going to read the 4 different cows. And what is interesting is that, they pointed out the need to understand variation, and that variation can be really huge among individuals. And that's a big critiques for the nutritionists, because generally we are very happy when we have like 12 animals or stuff like that. That may explain difficulty of collaboration with geneticists, and the relation with numbers is not the same, but this is quite interesting, and the question is not new. So this, as I said before, in animal nutrition, we were talking about nutrient partitioning much more than resource allocation, because finally, the view on the animal has evolved a lot in this discipline. Earlier on, the starting point was really to see the animal as a biochemical converter. It's a flow of material from the environment. The animal is the passive transformator producing something. And in this view, nutrient partitioning is the consequence of a production potential. A scheme is easier to explain that. So you have your environment. Okay, you can't see anything. So you have the environment, the animal, our biochemical converter, intake some resource from this environment, partition, produce milk. And here, milk and meat, generally, that's the way we see production potential. The sheep has a average daily gain potential of, or the goat has a milk production potential of 2-3 kilograms of milk, and so on. Based on this production potential, we compute requirements, because we analyze gas exchanges and heat production and all the stuff, so we can compute, okay, to produce this, we need this amount of energy. So to satisfy these requirements, the animal needs to intake this amount of food. Given that we have quantified the feedstuff in the same unit as requirement, we are able to make the balance. And if there is deviation, here we can compute the deviation in animal response to the diet. That's the way nutritionists are seeing how an animal is transforming a diet. So biochemical view. And you can see that in a lot of models. So here it's a historical model from US on dairy cow, Baldwin. And everything is about biochemical stuff. So I don't know if you can read, but it's total absorbed amino acids, ammonia, propionic acid, all the stuff that you can love or not, that I don't really like. That's why I don't like to say I'm a nutritionist, because I don't really understand all of this. But you have all the biochemical operation within the cow, like plasma glucose is then lactate, and so on and so on. And we moved finally from this view to looking at our animals much more like active biological entity, and to consider that, no, it's not only a stoichiometric relationship between elements, the animal is regulated. And that's a scheme that tried to summarize it. So you have the diet that is transformed in a digestive operating system and a metabolic operating system. But this biochemical view is combined with a regulating subsystem that is moving the animal not only as a biochemical converter, but also as an active biological entity. And generally, we are considering 2 different types of regulation in nutrition. Homeostasis. Basically, it's what happens within your body right now. You have a glycemia regulation. And long-term regulation. the name could be homeoresis or teleophoresis. You may find different, or teleonomic regulation, but just to say that it's long-term regulation. And what does this really mean, this long-term regulation? It's to say that at one point, when an organism, especially female organism, when they change the physiological status, you need to have a coordinated changes of the whole metabolism of the female to move from instance, from a gestating status to a lactating status. So here you have a gestating female. So the tap here represents nutrient partitioning. So the female basically is gestating, so most of the diet is allocated to gestation and reserves. Then parturition happens. And now the female, the tap, is channeling all the resource toward lactation. And I could have even made something between the reserves and the lactation. So to support this change, like here the tap is channeling everything into gestation and reserves, and here we have everything channeled to lactation. You have a full coordination of hormones and all metabolites, and that is what we call the homeoresis regulation. So the key paper about that, it's the paper from Baumann and Curie, 1980. That really well explains these coordinated changes within the female organism. But if you look at that from a resource allocation point of view, it's not only like just a coordinated changes in hormones, it's a change in priority. Here the priority is to grow a gravid uterus. Here the priority is for the offspring to survive. So basically feed the offspring with milk. So from a female perspective, gestation to lactation, that's a change in priority. And this is, if you remember the beginning of my talk on the inherited allocation pattern, it's exactly the same for a cow, a sheep, or a goat. Male or female. I mean, this example is female because it's easier with female, but these changes in priority between function is just a reflect of the dynamics expression of genes. You're a female from a ruminant species. You are sort of programmed to switch at one point from gestation to lactation. This is what is called genetically driven trajectories. And yeah, if you have some question, you can ask Nick, because he was one of the nutritionists to push this idea that even if we are talking about nutrition, some stuff are genetically defined. And that was the starting point of connecting nutrition and genetics. And I'm back to the resource allocation theory book, because finally this book is from genetics. And the idea is like, are there any genetic differences in nutrient partitioning? Once you have explained that the traits are linked to this nutrient partitioning, it's interesting to see if there are some genetic differences. And again, this view on nutrient partitioning is very helpful to understand trade-offs among function. Because if you think to this female, starting the lactation, just switching from a previous physiological stage, generally, at least for dairy cow, less true for small ruminants, we are asking this female to go again in another reproductive cycle, while the priority of this female is there, not starting another cycle. So that may explain some trade-offs. And something very important, I'm repeating what has been said by other previous speakers, but the key role of body reserves to do that. And an example of this key role of body reserves, it's mobilization in early lactation. Because classical view, at least in my field, was to say that, okay, intake doesn't increase as fast as the requirement, so mobilization is a consequence. But if you look at some experimental evidence, it's impossible to completely cancel body reserves mobilization in early lactation. Even if you feed the animal with a very, very good diet, there is still a little bit of mobilization. It's because mobilization of reserves is part of the female strategy to support lactation. she has been selected for this, and there is an evolutive role of body reserves because it's a key aspect of resource allocation strategy for this female. And it's just a reminder that a dairy female is a mammal. Even if it's a mammal in a farm, it's still a mammal. So the question now that I said everything about that is that how can we integrate this level of regulation, so homeostasis regulation, long-term regulation, into nutrition model, and upscale this model at a lifetime level, because generally nutritionists are very good to predict an animal during the first month of lactation, parity 2, and blah, 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 but it's like a very tiny and short-term prediction, let's say. No offense, but if you need lifetime prediction, it's not enough to understand the first month of lactation. So you have basically two different approaches in nutrition. The bottom-up approach. So basically you consider that you will put your modeling effort at a low level, the level of the biological function, and you let regulation emerge at the whole animal level. So it's typically the model I presented earlier, deviation from the Molly Derrico model from the US. You have all the biochemical representation, and at one point something will happen and regulation will emerge. It doesn't work very well, to be honest, because this type of approach doesn't integrate the level of control we aimed at representing. So you have also other type of approach, top-down approach, where instead of considering that regulation will emerge, you impose the regulation. You consider that you want to represent that, so you will model that and impose that to your model. So Nix did a nice review in 2011 on that. You can check if you want to see the comparison between these two approaches. But let's say that here in the room you have a lot of people that are, I mean, me, Fred, and Nick, basically, I think. We worked a lot on that, on how to integrate this level of regulation into model. So I started years ago with the first version of dairy goat model, where I tried to have this operating system, a very traditional nutrition view on energetics, but combined with the first trial of regulating subsystem. A colleague from the lab developed something much more sophisticated here. Again, you have the reference if you want to check the paper, with really representation of priority. So it's completely conceptual. It's a set of compartments, and you have priority flowing, and you use this to control more biochemical view and more biochemical model. Another model is the one from Fred that he developed almost 10 years ago. And it's the same. It's a view here, not based on priority, directly based on allocation coefficient, like the resource obtained is split between body reserve deposition, then leftover is pregnancy, then leftover is for lactation, and so on. And today, we will see the recent, not so recent as well, but the model I developed for dairy cow. It's currently under adaptation for dairy goats, but we will play with the dairy cow version because I needed you to play with a stabilized version. So it's going to be the dairy cow version. But the concept is exactly the same. And I developed this model in collaboration with some people from ecology. Because finally, in ecology, they do have the knowledge on allocation, but they miss all the data on nutrition. I mean, they can't run experiment with a squirrel or stuff like that. And so there is a very good complementarity between these two areas. So it was a very, very interesting collaboration with the colleagues, so Denis Réal, and this paper is based on this, has been the starting point of developing this model. And this is the idea. Based on this approach, So the name of the model is ACAL. I'm not very original to find names for model because it's acquisition allocation in French. So ACAL, basic, but. And we will see that in the next part of the afternoon. And what you need to maybe keep from this first part is that this model translates an effort of really splitting allocation on one side and acquisition on the other side. Because if we're back on this idea of studying feed efficiency, we want to understand variation here, so at an aggregated level. So it's important to be able to understand variation here and variation here. Utilization, there is less variation, biological variation. So that has been the whole idea behind developing this model. And just a little bit about resilience, because so far my talk was very much about feed efficiency, but Smarter is about also resilience. So you've seen a lot of resilience aspects this morning. So resilience can be defined in many ways, but let's say ability to cope with a short-term challenge or deviation from a baseline trajectory induced by a perturbation. And the idea is that allocation models are able to provide this baseline trajectory. So this is the link I can make with resilience. And two important things, I think that Nick said that this morning. If you want to understand how the animal is deviating from the trajectory, you need to know what is the state of body reserves at the time of perturbation. So it's kind of an accumulated story. And maybe there will be a reallocation of nutrients, but if you want to reallocate, you need to know how it's allocated. It's basic, but this is the link we are making. And I also used the figure from the paper from Marieke, Popper and colleagues, 2020. So we can say that allocation within modeling framework can help you providing the blue line. So the blue line can be obtained if you are using smoothing approach, but you can also use mechanistic model to provide this blue baseline and understand deviation. And to finish with this part, so as I said, we've been able to develop the model for the dairy goat version thanks to Smarter project. And still some research efforts are needed for health and reproduction function. That's the ongoing development on the model. And this is the end of this part of my talk, so for the introduction part. And now we will switch to the second part, like you will manipulate acquisition and allocation parameters to generate variability in trajectories. Of course, so the idea is that you get your hands dirty, I mean, really look at the code. But yeah, it's going to be tough because the time is pretty short, and I hope we won't have too many practical issues. If you want to know a bit more about the model we're going to use, I just add two references where you will find the full description of the model. But the idea for the next hour is really to play with the model to generate simulation and for you to understand how it works. That's okay, you're on, I can see on the first row, be careful, the more you go there, the less you will stay awake. So yes, just a bit of introduction about the model before you're going into the code and we try some stuff. So ACAL is for acquisition allocation, very original. So that's a dynamic model. So I don't know if you're used with dynamic model, but it's a dynamic model, so time is everything. Each time you generate something, and I don't put that on the graph, so that's an illustration of the output. The x-axis, it's time, or age. So the model is simulating the lifetime of here a dairy cow from birth to culling or death. That depends. And I told you about the nutrition background of the model. So basically, the model needs an environment based on dry matter offer and energy content. It transforms all of this resource to generate milk and body mass component outputs. The code incorporates 4 different components. So obviously, acquisition and allocation, and that's really the dynamic drivers. There is a whole part of the code which is very boring nutrition equations. And one part, quite important part, it's the reproduction probability, because there is a feedback in the model, like the female has a probability to conceive that is based on her own variable. This is the way we can introduce, for instance, feedback of reserves on reproduction. So if you want to simulate a cow, very important, you need to define at least 4 parameters. 2 are related to acquisition, so basically how many feed the cow can acquire from the environment. And 2 parameters reflecting the cow's strategy to distribute energy among functions. So you need to define these 4 parameters to be able to launch a simulation. And something important is that the number of lactation the cow will be able to do is a result of the simulation. It's emerging from the simulation. It's not something that you define prior to the simulation. And regarding the genetic context of using this model, so you can, one cow, let's say defining a cow implies to have 4 different values for 4 different parameters. So if you play with the values for this parameter, you're able to generate different cows, as you can see on the illustration on the right side of the slide. So that's a way to, I don't say genetic parameters because I know it's not the same in genetics, but it's genetic scaling parameters. You can use this parameter to make big cows, small cows, fat cows, thin cows, and so on. Okay, that's going to be the hardest part of the afternoon. Some general nutritional principle. I don't know, how are you familiar with gross energy, metabolizable energy, digestible energy? Not so much. Okay, let's say that if you take some feedstuff, you burn it, you get the growth energy content. That's really the basic stuff. So if you multiply the dry matter intake of your cow by this energy content, you know how many gross energy is entering in our biological system. But not all this energy is available because you have some lost in feces. Part of the energy can't be digested. And in ruminants, you have some lost through methane. So to get what we call the metabolizable energy, so the energy that can be used by biological function, you need to compute the growth energy intake. So what is the quality of my resource multiplied dry matter intake, and account for a proportion of loss in this growth energy. Well, here it's a static view, but as I say, imagine that this is for every day. This is computed in the model. Okay, next. So that's the metabolizable energy intake. This intake is split into functions. So survival, it's body reserves and maintenance. Growth, lactation, gestation. Principle, very, very basic. What is allocated to survival? It's what you eat, multiplied to the proportion you put into the function. This is not extraordinary. But in the end, when you do the sum of all the energy allocated to the function, this should be equal to what you eat, because there is no, we account already for some losses. So in the end, here, you should have energy conservation. Output equal input, so it means that this coefficient, this proportion, are equal to 1. And that's my best level of mathematics for this afternoon. This is my top equation system. Okay, now it's much more the nutrition stuff. So the metabolizable energy is used by a function. So basically lactation, we are talking about the mammary gland. So you have partial efficiency to transform metabolizable energy into net energy. Net energy is really what you get into your product, so the milk that is getting out of the cow, or the sheep, the goat. And this accounts for some heat production. And then, if you want to compute milk, because in the end we want to simulate milk production, you just divide the net energy that you allocate to the function by the standard value of 1 kilogram of milk. So kilocal divided by kilocal per kilogram is give you kilogram. So this is the whole chain of things to move from dry matter intake to finally milk. The whole point is that nutritionists worked for that, so all the coefficients are somewhere in literature or in feeding system, a bit the same for here, all the digestibility and all the stuff. But what we had to manage, it's much more this part on allocation. But before allocation, we need to acquire a resource. So here it's an example of what we consider as dry matter intake. So it's important for you to get this part because I said there is two components in acquisition. The first one is this one, the black line. This is basal acquisition. And so it's basically the amount of food that a cow can eat without any reproduction. So it's like the non-reproducing animal. Then you have, we consider in the model, that's an assumption, that the female is able to eat more during lactation. And if you play on the parameter behind this component, you play on the parameter, it's basically the asymptote of the equation. It's a sigmoid equation. You can simulate cow with low or high level of basal acquisition. So it's in kilogram per day. And the same for the acquisition during lactation. So just to illustrate you the type of equation for basal acquisition, what we consider as the GSP, genetic scaling parameter, it's this parameter in the equation. So changing this value enables you to change the level the animal is able to eat. So if you combine, and there is another GSP for this lactation acquisition, so if you combine the different values, you are able to simulate very different cows regarding dry matter intake. Allocation, it's a bit the same principle. So here you have time, so age of the animal in days, and here the allocation coefficient. So that's a proportion of energy. So it's something between 0 and 1. And you have one coefficient for each function. So growth, survival, which is maintenance and body reserves, lactation and gestation. So at the beginning of life, the animal basically has to allocate between two functions, growth and survival. And as long as the animal is aging, allocation to growth decrease. As the sum is always 1, allocation to survival increase. So that's always this system of the sum should be equal to 1. And then when gestation starts here, allocation to gestation increase, and as a consequence, allocation to survival decrease. So that's the way we are accounting for trade-offs. As soon as you allocate something for a function, the system retrieves something from another function. And, as I said, the structural constraint of this system is that the sum should be equal to 1. And so far, I'm playing with only two parameters that I consider as genetic scaling parameters, one for allocation to growth and one for allocation to lactation. And the same, you pick up high, low, the value you want for each of these equation, and you're able to simulate very different cows related their strategy of allocating to growth and strategy related to lactation allocation. So this is the way we are simulating the different dynamic of priorities among functions. How much energy is allocated to the function. How do we did that? I'm going to be fast on this aspect because it's the boring mathematical aspect. It's a compartmental structure. So we use 4 different compartments. Each compartment represents one function. So one compartment for growth, survival. PF stands for future progeny. It's an ecological way to define gestation. And PC stands for current progeny, which is an ecological way to define lactation. At any time step, and we considered that there is a virtual quantity of 1 that is flowing into this system. So you have like pipes between compartments, and everything is flowing in that. And as it's closed, there is no leak. We know that at any time step, if we are adding the value in each compartment, it's always 1, because we put 1 in the system, and nothing is in or out. So that's, I consider, a clever way to represent the structural constraints that we needed to keep the energy conservation between input and output. It's an ordinary differential equation formalism, so with numerical integration. Masoud talked a little bit about that this morning. It's not your concern right now. If you need more detail, you can ask me. But there is a numerical integration of all of this. So directly, the level of the compartments, back on the previous equation, it's what is multiplying ME intake to obtain what is attributed to the function. Well, that's a system dynamics approach. Forrester diagram, that's the family of the type of modeling here. And yes, the most important thing is how the flows are managed between the different boxes. And this is done with our genetically scaling parameters related to allocation, and some Boolean variable that will turn on the different flows. Because you understand that when the female is not gestating, there is no sense to activate the flow from survival to gestation or to future progeny. And that's a way, the fact that some parameters have the genetic scaling status, it's my choice. It's really the modeler choice. I could have put genetics everywhere, but it's already quite complicated to manipulate as a model. So I started with a humble version with only 4 parameters. But if you want to declare that, I don't know, a parameter somewhere is a genetic scaling parameter, no problem. It's just a modeling view on these parameters, but it's only parameters. I wonder, yeah, I'm almost at the end. So for you to get, because it's very fast to train you on dynamic modeling. So here, just an example with this gestation allocation. So here, it's the compartment allocation for survival, so maintenance and body reserves. And here, it's for gestation. At conception, there is a Boolean variable, gest status, very original name, that is becoming equal to 1, and that allows the flow to start. Before, it's 0, so there is no flow. And then, as the allocation to gestation value becomes not 0, the flow starts, and it's able, the model is allocating energy to gestation. Thanks to nutritionists and a lot of experiments, we are able to evaluate the cost of building 1 kilogram of graviduterus, so we can compute the change through time of the graviduterus. And this is how we are able to simulate the uterus mass depending on time, based on this energetic conversion. So you should imagine the flow from survival to gestation all along the gestation process, and then at parturition, we switch the gestation status to 0, then we cut the flow, and we took the quantity here, back here, because we still need to preserve this 1 constraint. And even if the flow stops, we need to be sure there is nothing here. Or you will always have some energy attributed to gestation. So that's a very, very short view on how the whole model is working. And finally, to be able to simulate the lifetime of the dairy cow, which is the objective of the model, you need an environment, because I told you the animal has a genetic scaling parameter for acquisition, but we need to know if the environment allows this potential acquisition to be achieved. And I talked about changes in physiological stage. So there are some individual biological variables. The cow has its own conception probability, depending on milk, body condition score, and energy balance. But we need to have a minimum representation of reproduction management. When it's possible, when it's not possible. And the same for the whole life of the dairy cow. You need a minimum representation of some culling rules, or you have forever living cow. Okay, I'm at the end of this part. So now, please finger crossed for the in silico part, because I hope that it will work on your own PC.